Searching is such a common thing to do that we have to know how to do it quickly. Now, we've talked before about the linear search, and if you remember, it just starts at the beginning of an array, and it looks at every consecutive element in the array until we find the target value, or until we get to the end of the array, and we realize, it's not in this array. But imagine doing this with a list of 10 million numbers, or 100 million numbers. It would take a ridiculously long time, especially if the elements are, for instance, strings. Because if you remember, to test whether two strings are equal, you sometimes have to compare every single character one by one. But if you remember from past discussions, we know that if we have the list in ascending order, in sorted order, then it's really quick to zero in on the target value or to determine that it's not actually present if we use a binary search algorithm. We'll show that this algorithm is on the order of log n in terms of its time complexity. We start off by looking in the middle of the list. Now, we might be lucky and we might find the search value right away. That would be great. But if we don't, we know whether to go on by searching in the first or in the second half of the list because we looked at the middle. And then we just reapply that technique over and over and over again. Key thing is this: every step, we're reducing the search region by a factor of 2. We're splitting our list in half. So soon we're either going to find the target value or we're going to narrow down the search to a single element. And if we do this, we can basically turn a list of 1 million entries into a result in at most 20 steps. Here you can see us performing a binary search on this sorted array. We're looking for the number 320, and at every step, you can see we highlight the sublist that might still contain our target, 320. Now, you'll also notice that at every step, we're making all the numbers invisible except for the middle of the current sublist, which is the one that we're comparing to 320. If we look at 205, we know it has to be greater, so the only sublist that's possible is to the right. The middle of that is 358. It's got to be less. Look at 301. Okay, it's got to be more than 301. The only element left then is 314, and that is not the target element, so we know our target is not in the list. And that's after only 4 steps. If the search value had happened to be 205 or 358 or 301 or 314, we'd have actually located it, we'd have found it in 4 or fewer steps. In fact, binary search is guaranteed to search a list of 15 sorted elements in at most 4 steps. Here you can see the relationship between the length of the list we're looking at and the maximum number of steps it takes to search through that list. If you want to be able to find the number in the second column, which is the maximum number of steps that we need, all you have to do is add 1 to the larger number in the first column's range and take the log base 2. Try it out with a couple. This shows us that any method using a binary search runs on the order of log n. So now we'll take a look at 2 versions of the binary search algorithm, 2 implementations, one of which is iterative and the other one is recursive. Both of these run on the order of log n, they're big O of log n, but we won't actually do a formal complexity analysis. Here you can see the iterative version. I encourage you to pause the video and read through this a little bit more carefully. The main gist of it is that we have 2 variables, left and right, which keep track of the current ends of the sublist that we're looking at. And those variables are being brought closer and closer together. Ultimately, when those 2 variables cross, or when they reach the same element, we know that we have reached the end of our algorithm. And at that point, if we found the element, perfect. If we haven't, we know that it's not present. Here's the recursive version. Again, I encourage you to pause the video and read through this a little bit more closely. It works in fundamentally the same way as the iterative version. You're using these variables left and right and midpoint in the same way. The only real difference here is that one is using a loop and the other is using recursion. It's not such a massive difference, at least in the philosophy of the algorithm. Again, pause the video and take a look when you have a second. If you'd like, copy these 2 methods down in a little program on your own. And if you'd like to run them, here's how you might do it. Again, pause this video, take a look if you'd like. But that's it for today. Binary search, very powerful searching tool.